Look up, gaze into the velvet darkness of the night sky, a canvas pricked with the diamond dust of 1 billion distant suns. For all of recorded history, this view has been our mirror, reflecting our questions, our fears, our aspirations. It is the ultimate context for the human story. We have told ourselves a comforting tale about this place, a story of uniformity, of a grand cosmic democracy. The narrative insists that our location, our galactic home, is unremarkable, a typical address in a universe that, on the largest scales, looks the same from every vantage point. This is the principle of mediocrity, the bedrock of modern cosmology. It's a neat, orderly, and philosophically satisfying picture. But what if this story, the one we've been told for a century, is built upon a profound misunderstanding? What if our cosmic address is not typical at all? What if the very fabric of our reality, the space for billions of light years around us, is an anomaly, a place fundamentally different from the great beyond? Imagine discovering that the city you've always known as the world is actually a secluded village in a vast, uncharted desert. This is the story of a monumental cosmic secret. A revelation that we are adrift inside a colossal hole in the universe, and until recently, nobody even knew to tell us. Our quest to understand this secret begins not in the cold void of space, but in the warm glow of human curiosity. Centuries ago, for millennia, the universe was a cozy, intimate affair, a celestial sphere, perhaps, with the Earth held firmly at its center. The stars were fixed points of light, divine decorations on a celestial ceiling. This was a universe made for us, a stage for the human drama. The revolution began quietly, with meticulous observations and courageous mathematics. Copernicus, Kepler, and Galileo dismantled this geocentric comfort, displacing humanity from the heart of creation. With the invention of the telescope, our cosmic horizons began to recede, revealing a universe far larger and more complex than we had ever conceived. Our sun became just another star, and our solar system a minor outpost. The next great leap into the cosmic ocean occurred in the 1920s, atop Mount Wilson in California, where a man named Edwin Hubble was systematically charting the faint, hazy patches of light known as nebulae. The prevailing wisdom of the time held that these were nascent solar systems, swirling clouds of gas within our own Milky Way galaxy. But Hubble, using the colossal 100-inch Hooker telescope, found something that would shatter our perception of reality. Within the Andromeda Nebula, he identified a specific type of star, a Cepheid variable, a pulsating star whose rhythm is intrinsically linked to its true brightness. It was a standard candle, a cosmic yardstick. By comparing the star's apparent dimness to its known intrinsic luminosity, Hubble could calculate its distance. The number he found was staggering. Andromeda was not a nearby cloud. It was nearly 1 million light-years away, an island universe of hundreds of billions of stars, entirely separate from our own. The universe had not just expanded, it had exploded in our minds. Our Milky Way was but one of countless galaxies scattered through the depths of space, but Hubble's most profound discovery was yet to come. As he measured the distances to more and more of these galactic islands, he noticed a peculiar, universal pattern in their light. The light from almost every galaxy was stretched, shifted toward the red end of the spectrum. This was the Doppler effect, the same phenomenon that makes an ambulance siren sound lower in pitch as it speeds away from you. The galaxies were not stationary, they were all rushing away from us. And more astonishingly, the farther away a galaxy was, the faster it receded. The conclusion was inescapable, world-altering. The very fabric of space-time itself was expanding. The universe was not a static stage, but a dynamic, growing entity. A common analogy is that of a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others appear to be receding, and the more distant ones move away faster. There is no center to the expansion. It is happening everywhere at once. This discovery gave birth to the Big Bang Theory, and established a new cosmic dogma, the cosmological principle. This principle states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means it has a uniform composition and density. No matter where you are, the average amount of stuff around you is the same. Isotropic means it looks the same in every direction. There are no preferred axes, no special alignments in the cosmos. Our raisin, in other words, is no different from any other raisin. Our view of the expanding universe is the same view anyone, anywhere would have. This principle was not just an elegant theory. It became the fundamental assumption, the starting point for nearly all of our models of the universe. As our technology advanced, we began to map this universe in 3 dimensions. Vast surveys painstakingly measured the positions and redshifts of millions of galaxies, painting a portrait of the cosmos on an unimaginable scale. What emerged from these maps was not a uniform, featureless distribution of matter. Instead, it was something far more intricate and breathtakingly beautiful. The universe, on the largest scales, is structured like a sponge or a neural network. Galaxies are not scattered randomly like dust. They are drawn together by gravity into unimaginably long, glittering filaments and dense, crowded intersections. These are the superclusters, the great metropolitan hubs of the cosmos, teeming with thousands of galaxies, each a city of billions of stars. These filaments connect to one another, forming the walls of a colossal structure that astronomers have poetically named the cosmic web. It is the largest known structure in existence, a luminous tapestry of matter, woven across hundreds of millions of light years, a glowing skeleton of creation. It is a picture of sublime complexity, a universe of breathtaking architecture. But this grand tapestry also reveals a profound emptiness. For every glittering filament and every dense supercluster, there are vast, dark, and astonishingly empty regions that separate them. These are the cosmic voids. They are the great deserts of the universe, immense bubbles of near-nothingness. They are not truly empty. They still contain a sparse scattering of galaxies, lonely drifters in an ocean of quiet desolation. But their density is a fraction of the cosmic average. While the filaments are the bustling highways of the universe, the voids are the silent, forgotten backwaters. For decades, we saw these voids as mere gaps in the cosmic web, the spaces between the interesting parts. We mapped them, catalogued them, and assumed we lived far from them, safely nestled within a typical, unremarkable strand of the cosmic web. That assumption, it turns out, may have been the greatest mistake in modern cosmology. The first hint that something was profoundly wrong with our standard story came from a persistent and deeply troubling disagreement, a mystery that cosmologists now call the Hubble tension. It is a conflict born from our 2 most powerful methods of observing the universe, a schism between the cosmos in its infancy and the cosmos as it is today. The problem revolves around a single number, the Hubble constant, a figure that represents the current expansion rate of the universe. Measuring this number has been a holy grail of astronomy for a century. The first method is to measure it directly, here and now. This is the local measurement, a technique that builds upon Edwin Hubble's original work. It's called the cosmic distance ladder, and it requires astronomers to meticulously measure distances rung by rung out into the universe. The first rung relies on parallax, a form of cosmic triangulation for nearby stars. The next rung uses those Cepheid variable stars, the pulsating beacons, first used by Hubble, whose rhythm betrays their true brilliance. By calibrating Cepheids in our own galaxy, we can then find them in nearby galaxies and determine their distances with incredible precision. The final rung of the ladder uses a much brighter, much rarer event, a Type Ia supernova. These are the thermonuclear explosions of white dwarf stars, and they are astonishingly consistent. Each one detonates with nearly the same intrinsic brightness, making them the ultimate standard candle, visible across billions of light years. By finding galaxies that host both Cepheids and these supernovae, we can calibrate the brightness of the explosions. Then, we can look for these cataclysms in the far-flung corners of the cosmos. to measure the expansion rate deep into cosmic history. Led by Nobel laureate Adam Rees, teams have spent decades refining this method, using the Hubble Space Telescope and other observatories to build a robust, high-precision measurement of the local expansion rate. The number they have settled on is approximately 73 kilometers per second per megaparsec. This means that for every 3.26 million light-years you travel away from us, the universe is expanding 73 kilometers per second faster. This number seems solid, a triumph of observational astronomy. But there is another way to determine the expansion rate, a way that does not look at the universe today, but at its very beginning. This second method involves studying the oldest light in existence, the faint afterglow of the Big Bang itself. This is the cosmic microwave background, or CMB. It is a faint, pervasive hum of radiation that fills all of space, a snapshot of the universe, when it was a mere 380,000 years old. Back then, the cosmos was a hot, dense, opaque fog of plasma. As it expanded and cooled, atoms formed, and the universe suddenly became transparent. The light that was present at that moment was finally set free, and it has been traveling across the cosmos ever since, its wavelength stretched by cosmic expansion from brilliant light into cool microwaves. Satellites like WMAP, and more recently, the European Space Agency's Planck Observatory, have mapped this ancient light with extraordinary sensitivity. The CMB is not perfectly uniform. It is dappled with minuscule temperature fluctuations, tiny ripples that represent the seeds of all future structures. These ripples encode a wealth of information about the early universe. They tell us its age, its composition, the precise amounts of dark matter, dark energy, and ordinary matter, and crucially, they contain a prediction. Contained within this baby picture of the universe is a complete cosmological model known as lambda CDM. This model, our standard model of cosmology, is incredibly successful. And when you feed all the precise data from the Planck satellite into this model, you can calculate what the expansion rate of the universe times should times be today. It allows you to wind the cosmic clock forward 13.8 billion years. And this is where the crisis begins. The number predicted by the Planck data and our standard model of cosmology is not 73. It is approximately 67 kilometers per second per megaparsec. These two numbers do not agree. They are not even close. The error bars on both measurements are now so small that there is no overlap. The chance that this discrepancy is a statistical fluke is less than 1 in a million. This is the Hubble tension. It's a tale of two universes. The early universe, observed through the CMB, is telling us one story about how it should be expanding today. The local, modern universe, observed through supernovae, is screaming a different story. Something is wrong. Either our measurements of the local universe are flawed, our understanding of the early universe is mistaken, or the cosmological model that connects the two is incomplete. For years, cosmologists have searched for errors in the measurements, recalibrating their yardsticks, reanalyzing their data, but the tension remains. It has become the single biggest crisis in modern cosmology, and it is not the only strange clue that our cosmic neighborhood is unusual. Another anomaly lies imprinted on that same baby picture of the universe. When astronomers studied the Planck map of the CMB, they found something that, by all rights, should not be there. In the direction of the constellation Eridanus, there is a patch of the sky that is anomalously, inexplicably large and cold. This isn't just a minor fluctuation, it is the most significant deviation from statistical randomness on the entire map. Known as the CMB cold spot, it is a chilling fingerprint of something immense. Initial, more exotic theories suggested it could be a bruise from a collision with another universe, a cosmic texture, or a flaw in the fabric of space-time. But a far more mundane, yet no less profound, explanation has since gained traction. The cold spot might be an illusion, a trick of cosmic geography. It could be caused by the light from the CMB having to travel through an exceptionally large and empty region of space on its way to us. This is a phenomenon known as the integrated Sachs-Wolf effect. Imagine a photon of light as a marble rolling across a rubber sheet. If the marble rolls into a dip representing the gravity well of a galaxy cluster, it gains energy and speeds up. As it climbs back out, it loses that same amount of energy, emerging with its original momentum. But if the universe is expanding and dominated by dark energy, the gravity well becomes shallower while the photon is inside. So, when the photon climbs out, it doesn't have to work as hard. It leaves with a net gain of energy, appearing slightly hotter or blue-shifted. Conversely, if a photon travels through a vast void, a region with less mass and thus a sort of anti-well or hill in space-time, the opposite happens. As the photon enters the void, it loses energy, climbing the gravitational hill. While it's inside, the expansion of the universe stretches and flattens the hill. So when the photon rolls back down the other side, it doesn't regain all the energy it lost. It emerges from the void with a net energy deficit, appearing slightly colder or redshifted. The CMB cold spot could therefore be the ghostly signature of a truly colossal void, a billion light-year-wide chasm in the universe, sitting directly in our line of sight. Surveys of galaxies in that direction have indeed found such a structure, the Eridanus supervoid. But even this gargantuan emptiness is not quite large enough to fully account for the temperature of the cold spot. Unless that supervoid is merely a part of something much, much bigger. Something that doesn't just lie in our line of sight, but that completely surrounds us. This brings us to the precipice of a radical and transformative idea. An idea that connects the Hubble tension and the cold spot, tying these disparate clues into a single, cohesive narrative. The hypothesis is this: the Milky Way, our entire local group of galaxies, and indeed our entire Laniakea supercluster, are all located inside one of the universe's great cosmic voids. We are living in a cosmic hole. This proposed structure is known as the KBC Void, named for the astronomers Ryan Keenan, Amy Barger, and Lennox Cowie who first proposed it. It is a bubble of underdensity, of almost unimaginable proportions. Its estimated diameter is a staggering 2 billion light-years. It is one of the largest structures ever conceived. To call it a hole is perhaps misleading. It is not a perfect vacuum. It is a region of space that is simply 20 to 50% less dense than the average of the universe as a whole. It is a cosmic basin, a vast, shallow valley in the topography of the cosmos. Imagine the cosmic web is a magnificent, sprawling forest. We have always assumed we lived in a typical grove, surrounded by trees. This new idea suggests we actually live in a gigantic clearing in that forest, a meadow so vast we couldn't see the tree line for generations. How could such a monumental structure solve our greatest cosmic puzzles? Let's start with the Hubble tension. The solution is a matter of perspective, a consequence of gravity and location. If we are inside a colossal, underdense bubble, then the regions outside the bubble, the dense walls of the void, contain significantly more mass. This means the matter outside our bubble exerts a stronger gravitational pull on everything inside the bubble than the sparse matter within it does. This creates a powerful net outward force. It is like being in the center of a giant, spherical trampoline, where heavy weights have been placed all around the distant rim. The fabric of spacetime in our local area is being stretched outwards by the gravitational attraction of the denser universe beyond our void. This local outflow, this gravitational tide pulling us toward the void walls, is a motion that is entirely separate from the global expansion of the universe. It is a local current in the great cosmic river. So when we measure the recession of galaxies from our vantage point, we are measuring two things at once. We see the uniform, global expansion of space-time described by the Big Bang, the 67 value predicted by the CMB. But on top of that, we are also measuring this additional, local, outward flow. The two effects combine. The local flow effectively inflates our measurement of the global expansion. It makes it look times like the universe is expanding faster from our perspective than it actually is on average. The 73 value is not the true Hubble constant. It is a locally biased measurement, contaminated by the fact that we live in a cosmic hole. The Hubble tension, in this scenario, is not a tension at all. It is a direct consequence of our atypical address in the cosmos. The early universe measurement from the CMB gives us the true global average expansion rate. Our local measurement using supernovae gives us a higher, provincially inflated value. Both measurements can be correct. It's our assumption, the cosmological principle, that was wrong. We assumed our view was typical, but it is not. We are being pushed and pulled by local structures in a way that creates a cosmic mirage. This single, elegant idea also naturally enfolds the other great anomaly, the CMB cold spot. If we are in a giant void, then it is not surprising to find other large voids, like the Eridanus supervoid, nearby. Our location within this vast basin could mean that the path of the CMB photons from the cold spot's direction has been traveling through underdense regions for longer, losing more energy, and thus appearing even colder than a single void could explain. Our local environment becomes the missing piece of the puzzle. The implications of this hypothesis are nothing short of revolutionary. It represents a direct challenge to the Copernican and cosmological principles, the very idea that we are not in a special place. The Copernican revolution taught us we are not at the center of the solar system. Hubble taught us we are not in the central galaxy of the universe. The cosmological principle was the final step, asserting that our location has no significance whatsoever, but living inside one of the universe's largest voids times is times special. It makes our position cosmically relevant again, not in a privileged, central way, but in a specific, anomalous way. We are back on the cosmic map, not as the capital, but as a strange and remote province. This shift in perspective forces us to reevaluate everything we think we know. Consider dark energy. Its discovery, the observation that the universe's expansion is accelerating, was based on those same type Ia supernovae. Astronomers noticed that distant supernovae were dimmer than they should be, in a universe expanding at a constant rate, implying they were farther away than expected. This led to the conclusion that the expansion had sped up over time, driven by a mysterious repulsive force called dark energy. But if our local measurements have been contaminated by our presence in a void, it could alter our calculations of this acceleration. The apparent speed-up might be, at least in part, another illusion. Perhaps we don't need as much mysterious dark energy as we thought. The behavior of the universe could be explained more by its structure, by the hills and valleys of the cosmic web, than by an enigmatic new force. The philosophical and even existential questions are profound. What does it mean for life to have emerged in a cosmic backwater? Is it a coincidence? Or is there a deeper connection? Perhaps voids are, counterintuitively, more hospitable to the development of complex life over billions of years. The dense filaments of the cosmic web are violent places. Galaxies are constantly colliding and merging, triggering massive bursts of star formation and bathing their environments in lethal radiation from supernovae and active galactic nuclei. A quiet, underdense void might be a safer harbor, a more stable environment where a solar system can evolve in relative peace for eons, undisturbed by cosmic cataclysms, providing the long, uninterrupted quiet necessary for biology to perform its slow, intricate work. Perhaps we are not just in a void, but times from times a void. Our existence could be a testament to the virtues of cosmic solitude. Of course, such an extraordinary claim requires extraordinary evidence. The idea that we live in a cosmic hole is still a hypothesis, and it faces skepticism. Many cosmologists believe the Hubble tension points not to a flaw in our assumptions about location, but to a flaw in our understanding of physics. Perhaps there is some new particle, some unknown interaction in the early universe that has been overlooked in our standard lambda CDM model. This new physics could have altered the expansion rate in the universe's youth, reconciling the two measurements without having to sacrifice the cosmological principle. The debate rages on, a vibrant and essential process at the heart of science. The final verdict will come from the next generation of cosmic cartographers. observatories like the Vera C, Rubin Observatory in Chile, and space telescopes like the European Space Agency's Euclid mission are designed to create the largest, deepest 3D maps of the universe ever attempted. They will chart the positions of billions of galaxies, painting a definitive picture of the cosmic web and its voids. These surveys will either confirm the existence and scale of the KBC Void, showing that we are indeed in a vast underdensity, or they will show that our cosmic neighborhood is, in fact, average, forcing us to look for new physics to solve the Hubble tension. The James Webb Space Telescope is also playing a crucial role, refining our measurements of the cosmic distance ladder with unprecedented accuracy, ensuring that no subtle error has led us astray. We stand at a pivotal moment in our understanding of the cosmos. The comfortable story we told ourselves for a century has begun to unravel. The clues are scattered before us. A cosmic expansion that refuses to be pinned down, a cold spectre haunting the dawn of time, and the tantalizing possibility that our entire world is an anomaly. The journey to this point has taken us from a small, Earth-centered stage to an expanding universe of infinite complexity. And now it has led us to question the very ground beneath our cosmic feet. Look up at the night sky one more time. The light from those distant stars and galaxies has travelled for eons across the vast, structured ocean of space-time. Its journey has been shaped by the invisible gravity of dark matter, stretched by the relentless expansion of the universe, and perhaps deflected and drained by the immense, silent voids that dominate the cosmos. We are not just looking out at the universe, we are looking through it, through its history, its structure, its secrets. The story that nobody told us is the one we are only now learning to read in that ancient light. It is a story that suggests we are children of the emptiness, inhabitants of a great cosmic clearing, and if this is true, it does not diminish our place in the universe. It makes it all the more remarkable. It means our search for understanding has, by a strange quirk of cosmic fate, begun from one of the quietest, most unique places in all of existence. And from this serene vantage point, we continue our endless, humbling quest to comprehend it all.